We've been focusing on trigonometry through the lens of automotive contexts. I chose cars as a topic because I believe in learning the most complex aspect of a subject first. By mastering the challenging parts, I can later scale back and apply that knowledge more specifically to whatever project or idea I'm working on. This approach is inspired by polymaths, figures like Leonardo da Vinci and Michelangelo, who excelled across multiple disciplines in both the arts and sciences. Other polymaths, like Aristotle and Archimedes, combined philosophy, mathematics, and natural sciences, serving as natural philosophers who merged theoretical knowledge with practical applications. On my channel and in my work, I strive to adopt a similar multidisciplinary approach. In today's world, to succeed, it helps to be somewhat of a polymath, to integrate insights from various fields. Personally, while I work in mechanical engineering, particularly in drafting and design, I also have a passion for applying these skills in other areas, like fashion design. This holistic, interdisciplinary approach allows for greater creativity and problem solving. In fields like business, for instance, this integrated perspective can create unique offerings that resonate deeply, reducing the need for heavy marketing because the concept itself is already compelling. Moving on to today's topic, kinematics and dynamic systems within mechanical engineering. Mechanical engineering, in many ways, forms the foundation for other engineering fields. Kinematics, specifically, is the study of motion without considering the forces involved. It calculates the positions, displacements, velocities, and accelerations of system components without accounting for the forces behind them. This is why I made a previous video on linear equations, and why we're studying trigonometry in automotive contexts. It's a great way to understand complex kinematic systems in a practical setting. I find it useful to start with complex concepts and then break them down. For example, when learning about kinematics, geometry provides a literal frame of reference. Within this framework, we work with axes, triangles, and the unit circle, which allows for rotation and deeper conceptualization. Understanding these geometrical structures helps us visualize kinematic concepts, like displacements and velocities, within familiar shapes. It's crucial to have a conceptual framework, otherwise, it can be confusing to handle abstract calculations. This approach helps distinguish kinematics from related fields, such as statics and dynamics. By using geometry as our foundation, we can make sense of kinematic relationships, applying trigonometry and calculus to calculate positions and movements within a clear visual structure. This way, we're not just doing math, but using shapes and frames of reference to grasp the relationships in motion and mechanics. There are three main areas of focus: statics, dynamics, and kinematics. 1. Statics. This involves analyzing motion and loads according to Newton's first law, which means that the forces in the system are balanced, or in equilibrium. In statics, the goal is to ensure all forces are equalized to maintain stability in the system, preventing it from collapsing. 2. Dynamics. This field considers motion and governing loads based on Newton's second law, where forces cause acceleration. While statics is about balancing forces, dynamics addresses situations where forces result in motion. For instance, think of the engine inside a car. Combustion creates force, which leads to the rotation of the tires and ultimately accelerates the vehicle. This is a classic example of a dynamic system where forces directly influence movement. 3. Kinematic. This focuses solely on motion, independent of the forces causing it, making it fundamental in mechanical system design. It's often the first step in the design process, especially in engineering contexts like automotive systems. Before diving into kinematics, we covered trigonometry in the context of cars to build a strong foundation. Kinematics helps us understand how components will move without yet considering the forces driving them. After addressing kinematics, we shift focus to statics and dynamics to evaluate loads. For example, kinematics in a camshaft system converts rotational motion into linear motion, which drives another component up or down based on the cam's unique profile. This geometry-based approach controls the follower's speed, timing, and movement, like adjusting acceleration or deceleration. Designing with kinematics can be highly creative as you explore different shapes and motions that achieve efficient energy use. Once you've designed a feasible kinematic system, the next step is to evaluate the loads with statics or dynamics. This stage involves heavy experimentation and math to refine the design. While kinematics involves calculations, it often leaves room for creativity since it relies on physics and geometry. It's the interplay between kinematics, statics, and dynamics that brings a design to life. I wanted to quickly share something that I posted on Instagram. I often archive my posts because they're really more for me, a way to remember things. Even though I put them out there, it's mainly so I can revisit them if I lose access to my accounts. Sometimes it's hard for me to articulate things, so I often write down notes to help. The video was, a wise older man, though I can't remember his name, that he has to write things down or he feels lost, even to the point of feeling depressed. This resonated deeply with me because, for years, I've experienced something similar. We humans are forgetful, we can lose sight of who we are, what we're doing, and where we're headed. Life is chaotic, and the past can cling to us in ways that make moving forward hard. Writing things down, talking about them, and reflecting helps us hold on to ourselves. Now, on to the technical part. After determining if a design's movement is feasible, kinematic feasibility, we consider the forces involved, static or dynamic loads. This is where stress analysis comes in, evaluating how materials will respond to these forces, which helps ensure they won't break and can endure over time. Factors like material choice, thickness, and cost all play a role here. The process of designing mechanical systems starts with kinematics, followed by statics and dynamics, stress analysis, and finally, machine design. Each step builds on the last to create a functional design. For example, kinematics lays the groundwork, and everything else, like static and dynamic forces, are analyzed based on this foundational movement. In terms of abstract thinking, our understanding of geometry and physics shapes the way we design. Concepts like rotational and linear motion, often seen in mechanical systems, translate one type of movement into another. Take pliers, for instance, moving one handle moves the other through a joint, resulting in a gripping action. This is a kinematic chain, a sequence where each link's movement is influenced by the last. In complex systems, like car engines, multiple kinematic chains interact, each link designed for specific movement. A tool like pliers, however, may have just one chain, with movement resulting from the way it's held. Each part is interconnected, transferring controlled motion from one link to the next, and creating predictable actions. In such systems, we see the crucial role of grounding, which could be through friction, gravity, or bolts, making sure each part stays aligned with the frame of reference. Grounded links act as a foundation, much like the way we build knowledge. Just like with learning, one solid concept serves as a base, allowing other ideas to connect and form a cohesive understanding. For us, gravity is one of these grounded concepts, a constant we can rely on, anchoring all our calculations. So, in summary, kinematics is the foundation of any design, followed by statics, dynamics, stress analysis, and machine design. The kinematic analysis, or study of movement, then informs kinematic synthesis, which is the design process itself, ensuring each component moves exactly as planned. From simple tools to complex systems, this approach helps us achieve reliable, precise, and controlled movement. By grounding each link to a consistent reference, like gravity, we ensure stability, predictability, and ultimately, a well-functioning design. A grounded link is a component fixed to a frame of reference, which could be a physical frame or the ground itself. This grounded link provides stability in a base, allowing all other motions in the linkage to be referenced back to it. By anchoring the mechanism, it establishes a stable origin that defines the motion path of every other link in the system. Think of it as the foundation, like the starting point in trigonometry that anchors calculations involving right triangles and angles around the unit circle. It's the origin point where the x and y axes converge, setting the stage for all other angles and forming the basis of the geometry. Geometrically speaking, this anchor is essential for visualizing and constructing right triangles within a graph. So, the grounded link both stabilizes the mechanism and defines the motion for all other links. This concept becomes essential when we delve into geometry or trigonometry. The grounded link also absorbs forces exerted by other links during operation, keeping the entire system steady. This means the grounded link must be the strongest part of the system, both in material strength and in the way it's positioned and linked. It's almost like the body of Christ. Within the system, it absorbs and withstands all stresses so that the system as a whole can function properly. For example, in a pair of pliers, the grounded link might be the handle you hold steady, which stabilizes the tool. This grounding lets you apply controlled force to the other handle, which moves the jaw for gripping. In more complex machinery, grounding is often achieved by securely bolting or fastening the link to a stable structure to prevent movement, allowing all other parts to operate relative to it. You could also think of a tent. When you set it up, the stake you drive into the ground, connected by rope to the tent, serves as a grounding anchor. This anchor prevents movement in windy conditions by securing the tent to the ground. Thus, the grounded link serves as a fixed reference for stability in a mechanism, while the linkage is an interconnected assembly of moving parts that rely on this grounding to perform controlled, desired motions. Leonardo da Vinci's mechanical designs exemplify this principle well. His sketches, such as those for automata and various machines, demonstrate an early understanding of linkages and grounded pivots to achieve efficient motion. These designs feature intricate arrangements of spiraling pivots and gears that store, transfer, and even amplify energy through their geometry, creating mechanical advantages. This geometry allows for reduced force needed to initiate or sustain movement, which in turn saves energy by optimizing force distribution. Leonardo frequently used spring mechanisms alongside spiraling pivots or weights to store energy and release it in a controlled manner, similar to how a clock escapement mechanism provides a steady output over time. For instance, consider the springs in a mattress. They compress under weight, storing force in a compact way, and release it smoothly when lifted. Leonardo also explored compound linkages where smaller interconnected pivots allow for complex compounded movements with minimal input. This design enables multiple parts, like arms in his robotic knight, to move in a synchronized, efficient manner. When we think of Steven Spielberg's movies, like The Goonies, we often see sequences where a single force sets off a chain reaction, a rolling bowling ball, for instance, triggering motion in one object after another. This kinematic chain mirrors how cars work. A single explosion in the engine initiates a cascade of controlled forces that propel the vehicle efficiently. Similarly, Leonardo da Vinci's designs laid foundational principles for understanding mechanical efficiency through geometry. His work on linkage systems and grounded pivots still informs modern machinery, robotics, and energy-saving devices. For instance, his robotic knight, built in 1495, is one of the earliest humanoid automata. This mechanical knight, reconstructed from Leonardo's drawings, could sit, stand, move its arms, and even open its mouth, demonstrating his advanced grasp of mechanics through gears, pulleys, and cables. Engineer Mark Elling-Rosheim recreated this robot in the 1990s, bringing Leonardo's designs to life with incredible detail. I actually have Rosheim's book, Leonardo's Lost Robots, which includes Leonardo's original sketches and showcases the recreations. Leonardo was a polymath, with knowledge in anatomy and physiology that informed his engineering. He didn't just memorize equations, he understood their essence, much like learning a coding language that goes beyond syntax to convey meaning. This holistic grasp allowed him to incorporate principles from biology and mechanics seamlessly into his inventions. His aerial screw design, for example, was a precursor to modern helicopter mechanics. Engineers today have even constructed motorized models of his designs, showing that Leonardo's principles were sound. In 2004, scientists at the Institute and Museum of the History of Science in Florence rebuilt his self-propelled cart, which used spring mechanisms and complex gearing, showing that Leonardo envisioned self-propulsion centuries before cars existed. His genius in kinematics is inspiring. Today, we have access to vast energy sources that, when combined with these principles, drive incredible efficiency. Leonardo's insights laid the groundwork for modern innovations, allowing anyone with vision and foundational knowledge to pursue similar interdisciplinary achievements. He also designed a mechanical lion for King Francis I of France that walked forward and opened its chest to reveal a bouquet of lilies. This automaton, built with a system of gears and clockwork-like mechanisms, highlights Leonardo's ability to blend art and mechanics. His robotics and automation ideas were not just imaginative, they were mechanically and mathematically sound, emphasizing kinematics, energy conservation, and force transmission. His work on robotic knights, self-propelled carts, and biomimicry continues to inspire engineers today. My own fascination with biomimicry started back in high school and early college, where I was captivated by biology, anatomy, and physiology. My love for engineering allowed me to transfer this knowledge into mechanical systems, much like Leonardo. His replicas, like those at the Leonardo da Vinci Museum in Italy, continue to educate and inspire, demonstrating how his interdisciplinary approach remains relevant to this day. Alright, Mr. Krabs, let's get this show on the road. And don't you dare cut that part out, or I swear, I'll split you like a green bean, one of those French ones, straight from the can. Imagine it split in half, that'll be you if you edit this out. Anyway, let's dive into mechanisms, specifically focusing on their mobility, or degrees of freedom, DOF. The degree of freedom refers to the number of independent parameters required to define a mechanism's unique position in space. Now, when analyzing mechanisms, you need to have enough parameters to fully describe each component's motion. Variables and their relationships, whether as components of a mechanism or grounding elements, are essential for thorough analysis and functionality. In 2D, planar motion, you need 3 independent parameters to define a body's position, 2 coordinates, x and y, and an orientation angle. For example, if you're parking a car in an xy coordinate frame, you need the car's x and y coordinates plus an angular position to know exactly where it's parked. This 2D framework, this geometrical space, is foundational. It's the same framework used in all scientific and mathematical conceptualization. When teaching, we often skip giving students a foundational spatial understanding, instead offering terms without concrete images, like stripping the idea of God from people's minds. In 2D space, mechanisms can have a maximum of 3 degrees of freedom. But in 3D space, 6 independent parameters are necessary, the 3 spatial coordinates, x, y, and z, and 3 orientation angles, one around each axis. These orientation angles allow us to define an object's spatial orientation. For instance, in a 3D space, these parameters allow you to visualize a cube, a space you can physically enter, unlike the flat planes of 2D. So, in 3D, you need those 6 parameters, the 3 coordinates, x, y, z, and 3 orientation angles to establish the position of, say, an aircraft in flight. Here's where trigonometry kicks in. Think of the unit circle, each angle defined creates a degree of freedom for the object, allowing it to move in that dimension.